Right, welcome back, everybody, and also welcome to Miss Sue. I see she's joined. Great, Korea. Uh, Andy will be continuing, and then I guess Brendan will be taking over on Tuesday next week. So anyway, go ahead, Andy.
Thanks. Thanks again, Jim and Anna, for setting this up and for people for attending. Um, so I figured I'd start with just a short recap of what we spoke about last time. So we're working in this superspace algebra, right, which is polynomial ring and variables tensored with an exterior algebra of rank n, these theta variables. And sometimes we'll call this S and E. And we're looking at this ideal of superspace invariance, which I don't think I wrote it down this way as precisely, but it'll come up today. You can write as kind of a power sum way, right? So it has two types of generators. One of these are exactly our power sums from the study of symmetric polynomials. And then we can hit each of them with the exterior derivative operator and introduce some of these anti-commuting variables theta. And we get one of these for each k equals 1 to n. Okay, so two n generators there. Um, or you can write them with, elementaries, all the usual games. Um, and the idea, right, was to look at the so-called J initial ideal of these things, to move this back into a polynomial question. So we have something like this. So what is this ideal? It's a polynomial ideal which consists of all the fj, where f is some element of the superspace invariance that looks like fj theta j. Uh, oh wait, let me write it like this. Where these are sets bigger than or equal to j in the kind of Lex order on subsets, so kind of using later indices. Um, and I guess f sub j should not be zero, so it's the first non-zero, the leading term here, right? Okay, I'll just write it like that. So this is our kind of Grosvenor style approach. And our claim that we're slowly working towards is that these J initial ideals have a nice presentation. Now I'm using elementaries, but I could write power sums here. Um, Using these elementaries as well as these other types of generators that look like this. Products of xi minus xj's for each little j in the set. And I guess I should write somewhere that j here is a subset of 1 through n. Okay. So to understand this superspace invariant ideal, we're going to understand 2 to the n many polynomial ideals, these initial ideals. And maybe it's worth stating that, okay, so this is our claim. Today we're going to at least sketch a proof of this containment, that everything on the right is in this initial ideal. Um, and I mean, in some sense, half of that is not so bad, right? So what about, the half involving these guys is pretty straightforward because, well, E sub I is in this superspace invariant ideal. It's in the usual polynomial invariant ideal, so it's certainly in this superspace one. And that means that if I just multiply it by a single theta sub j, this is um, an element of Si with leading term j and leading coefficient E sub I. Well, there's only theta j is the only monomial of thetas in that guy, which means that E sub I is in this initial ideal. Okay, so for disproving right to left containment, we're done with the E sub i's at least. But the others will be a lot more work. Um, how do we deal with the second type of generator? Any questions so far? This is kind of a recap. Okay, so the first thing we're going to do today is to prove this containment that these orange generators are J initial terms in SI, and we're going to use hyperplane arrangements to do that. So I'm going to kind of lay some groundwork about hyperplane arrangements. If you're familiar with hyperplane arrangements, I'm not going to say anything original for probably 10 minutes, but I will eventually say something original. Um, so a hyperplane, let me just kind of set some terminology. H in R sub n. This is a codimension 1 subspace. Of the vector space. So I'm just going to use linear hyperplanes, not affine ones. And given linear functional, alpha from V to R, linear form, right? We have an associated hyperplane that looks like the kernel of this thing, or more specifically, all the vectors that it sends to 0. So we can
Technically
take a linear
non-zero
functional.
linear functional.
Sorry, what's that?
Technically a non-zero linear
Oh, yes,
functional.
thank you. Yeah.
Yeah, it's okay.
Right.
It's okay.
Non-zero and linear functional, and these are only defined up to constant multiplication, right? Great, thank you.
Mhm.
Right, so we have a associated hyperplane, and also we have, maybe I won't write this out carefully, but given a hyperplane, we can get a linear functional up to a constant multiplication. So I'll just use that alpha sub h notation like that. Okay, then we have an arrangement of hyperplanes. I guess I'm using like a curly A. This is just a finite set of hyperplanes. And given such an arrangement, we have what's called the defining polynomial. This is written with a Q. This is just the product. Let's see, all the hyperplanes in the arrangement, we take their associated linear functional. So this is a polynomial, right? Only defined up to constant multiplication again, but product of linear forms, one for each hyperplane. So time for an example, I think. And in fact, in my piece today, I'm really only going to look at this braid arrangement. When Brendan takes over, he will use some related arrangements. But the braid arrangement, I'll write it as curly B, is the arrangement. So we take the hyperplane associated to a bunch of alphas, where alpha ij is xi minus xj. I is less than j. So there's n choose 2 if I'm working in V or Rn here. Many hyperplanes in this arrangement. Type A Coxer arrangement is another name for this. And its defining polynomial is the Vandermonde determinant. So we get this guy. Okay. So that's, I think, the first of many appearances of this thing in this lecture series. Okay, so this is mostly, if you want to think only about the braid arrangement, you'll be fine, at least for today. Next, we need to talk about derivations. So a derivation of first the entire polynomial ring, or maybe I should say the derivations I'll write them like this. There's various ways of defining this. I'm going to kind of skip a couple steps and just say it's the direct sum of a bunch of copies of S, each one paired with a partial derivative operator. So this is, this delta sub I is the thing that takes the partial derivative with respect to xi, right? Um, and this is an S module under pointwise operations. And more precisely, we're going to look at the derivations of a specific hyperplane arrangement. So given an arrangement A, we can look at the derivations of such an arrangement. And there's a few ways of writing this down. So you can write it as all the derivations that satisfy this property, that the defining polynomial divides what we get by applying each derivation to the defining polynomial. And I'll work through some examples of this in a second. Or another definition equivalently is, I maybe prefer the second one, is you can just look at each linear functional associated each hyperplane, and it divides what you get when you hit it by the derivation. So this is for every hyperplane in the arrangement. Okay. I'll hold off on my example for a second. Try to load a couple of other vocabulary terms first. So this is an S submodule of the derivations of all of S. And we're most interested in when this is a free module, right? So if this thing is free as an S module, then we say that alpha is a free arrangement, not alpha, A. And what do I mean by freeness? I basically mean it has a basis, right? So in this case, has an S module basis, which we can think of as a bunch of derivations, in fact, n of them, if we're working in n-dimensional vector space. And we can make them each be homogeneous as well. Degree, say d sub I. So, I mean, how to think about this? Most of us, I think, are coming from the world of combinatorics instead of the world of algebra. So free modules is where we can write down a basis. That's kind of, that's the good scenario. The bad scenario is what if you can't write down a basis and I don't know, it's more complicated, right? If you're an algebraist, maybe that's what you want to study, but as a combinatorialist, we're pretty happy in this world, I think. So these degrees are called the exponents of the arrangement. And one use of this theory is that they give you the product of adding 1 to these degrees or exponents gives you the number of regions or chambers in your arrangement. Okay. And they tell you lots more about this thing. Let me return to our example of the braid arrangement, right? So let's try to understand its derivation module. So what are some derivations of the braid arrangement? Well, I claim some of them, some elements look like, I'll write it as a rho sub k. And this should start to look familiar, right? This is going to be a power sum looking thing. Except instead of the theta i's from earlier, I've got these partial derivative operators. And why is this a valid derivation? Well, let's check that if we apply it to any linear functional, we get something which divides that, or is divisible by that linear functional, rather. So if we apply this to xi minus xj, right, these are the linear functionals that live in our braid arrangement. What do we get? Well, we get exactly this, right? Because this partial derivative operator, most of it evaluates to 1 on this guy and 0 everywhere else. So the only terms that survive look like xi to the k minus 1 and then minus xj to the k minus 1. And it is true, right, that xi minus xj divides this thing. Okay. So that's a check that such a thing lives in this module of derivations. In fact, they form a basis. So rho sub 1 up to rho sub n is a basis for the modulo of derivations. And this follows from something that sometimes called Saido's criterion. And I'll just kind of give you an example of what this means. So notice that we can kind of factor these like this. So we get for k equals 1, we get this. For k equals 2, okay. So this is another way of thinking about these rho sub k's. And that matrix is familiar, right? This is the Vandermonde matrix whose determinant is the Vandermonde determinant. And Saido's criterion roughly says that if you've got a set of the correct size to be a basis, so there's n things in there, and they're all genuinely in your module of derivations, which we just checked, they're all valid elements of the module. And if you write them this way and you take the determinant of this matrix, we get the Vandermonde, which remember is the defining polynomial of the arrangement, right? So if those things are true, you've got the right number of things, they're all in your module, and the determinant is the defining polynomial, then they must be a basis for the module. Maybe I need to assume it's free already. I can't remember.
I don't think you have to.
Okay,
No, you
then that
don't.
implies it's free
You
also.
don't. And also, it's sufficient for the determinant to be a scalar multiple of Q.
That's right. Yeah, all of these things are up to scalar multiple because the linear functionals are up to scalar
Right,
multiple. Thank you,
exactly.
Brendan and Bruce. Anything else I
So
missed?
it's just kind of one comment. When I saw the definition of derivation modules the first time, I was incredibly confused as to why this is an interesting thing to study. So you can think about polynomial derivations as vector fields, right, on in space. You would think about partial one, partial two, partial three as being like I hat, j hat, k hat, and so on, like in multivariable calculus. And derivations of an arrangement are those vector fields that are parallel to the hyperplanes of the arrangement. So that kind of gives you intuition as to, well, why is it that derivations of an arrangement form a submodule? And you can certainly check these things symbolically rather quickly, but for me at least, that was something that helped me kind of understand this theory a little bit better.
Yeah, this more geometric picture. Thanks. Any other comments or questions? That was a good place for them, so. Okay, so I'll write down one more basis for this module, and then you'll start to see where this shows up. So we can write these as psi sub k. So this is a little bit more complicated to write down. Oops. So what does this look like? So if we maybe just look at an example. Um, so let's see, when k equals 1, we get this again, I think. When k equals 2, the point should be that this is triangular, if I've written this down right. Um, so we get something like this. And what goes here is maybe this. Um, sorry, I got a little squash there. Something like this should be right. But the point is, well, it's definitely the right number of things. It's not obvious that they're actually in the derivation module, but you can check it. And certainly the determinant is the van der Waals determinant again, because now we can just take the product of these things. So this is starting to look a little bit more like these other generators we'd like to say something about, these orange things here. Okay. So how do we actually make this link to superspace invariance precise? We define some maps, right? So we define S module homomorphisms. I'll use this notation of just writing it as capital X. This goes from S derivations to superspace, where the partial I gets sent to X sub I. And I'll call this, I don't know, capital theta. What does that look like? Maybe like that. Where the partial I becomes a theta I. And then the claim is that, well, if you believe me that this row basis is indeed a basis for the module of derivations of the braid arrangement, then we can take X and apply it to the modulo derivations of the braid arrangement. we get our usual polynomial invariance. We can apply theta to the modulo of derivations of the Brane arrangement. We get the ones with the thetas in them, and this is the superspace invariant ideal. So we've got a new way of showing something is in the superspace invariant ideal. So if you can show it's in, you can come up with a derivation of the Brane arrangement, which gets mapped by either x or theta into, or sorry, if you can come up with something in the modulo of derivations, then hitting it with this map, you must land in the superspace invariant ideal. Okay. So then the proposition is that we can do this. Let me write down this proposition. So this is the part that I'm gonna skip over the details and maybe write up some more detailed notes. But let me just write it down. So given a set, maybe a non-empty set, capital J, and an element of that set, we claim just write down some elements of the superspace invariant ring using this strategy that I just outlined. So let's see. So and then we also need a last term here. So this is in SI. And the proof goes by arguing that it's an image of this, capital X plus capital theta map for some element of modulo of derivations of the Brane arrangement. And I mean, it's technical, but it's really just kind of a pure algebraic proof of just you write some things down, you verify it's in the modulo derivations, and then you get what you would like. Okay. And why is this what we want? Well, if we look at the leading term of these guys, that happens when r is equal to little j. So we get a little j here, which kind of fills in this gap here. And the j initial term of this then is starting to look a lot like these generators up here. And in fact, it is that. Okay. So this implies the remaining generators are in this initial ideal. Okay. And you're welcome to hold me to my claim that I can write up a detailed proof of this. I think I have it here in front of me, but I'd want to check it again before I shared it.
Andy, one question.
Please, yeah.
Yeah, so the theta sub j with little j deleted doesn't depend upon that product. So it could be on the other side, but you're writing it this way because when you do derivations, you want the derivatives in that order, or what? I'm not
But
understanding
I'm
why
not
you want
writing
it
it in
in
this way
this.
for any particular reason. Yeah, you're right that this up to a sign, right? Because these do anti-commute, you could move them around. Um,
Right.
yeah, I suppose the reason is that oh, I don't know. For me, it feels a bit more natural to have the derivative part sitting at the right, and then that hits the linear functional, but it's not for any important reason.
Okay. Just making sure I'm understanding.
Thank you. Yeah.
Sure.
That's right. Yeah, maybe you know,
For me, I would put all the thetas in one place and all the
no,
x's in
yeah.
another,
Ve-
but
Very
that's just
reasonable.
me.
Very reasonable suggestion. Any other comments or questions?
So just one little thing. So when you say SI is the image of x plus theta, SI is the ideal generated by the
Oh,
image.
thank you. That's right. Yeah.
Let's say that because technically, you're only living in fermionic degree at most one, but yeah,
Maybe
because
that's
you're hitting every generator of SI.
that's right.
So yeah.
Thank you. Yeah, something like that is better. Thanks. Oh, okay. Um, so Brendan will next week kind of develop these techniques a bit further, looking at other arrangements, braid-like arrangements, but not braid arrangements exactly, um, when trying to prove that this basis suggested by Sagan and Swanson is actually correct. Um, but this is all we need for now. Um, so if there aren't any other questions or comments, I'll move on. I have a couple more things to say to try to set Brendan up for next week, but so we've got this containment then. And what does that mean in terms of Hilbert series, right? Well, it means that the Hilbert series, this is the denominator, so you better reverse your inequality or whatever, but we have a bound on the Hilbert series in one direction, that the Hilbert series of this thing is no bigger than the products of Q integers of this associated lazy staircase. Okay. Okay, next I wanted to present this ideal another way. Um, so here's the main claim for this section, that this ideal we've been, well, I guess the right side of this kind of uh, claimed quality of ideals we've been looking at. I probably should have given a notation for this, but it's too late now. Um, is equal to a certain colon ideal. So I'll define what I mean by colon ideal in a second, but if you already know what that means, then you're in the clear. Um, okay, hopefully I got what I wanted to say here. So right. So what is a colon ideal? Given some ideal A, and these can be defined for two ideals, but I'll just define it for an ideal and a ring element. So A colon R is just all the things in the ring, such that when you multiply them by the ring element, you land in the ideal A. So they just need a little nudge to land in the ideal, and multiplication by R is this nudge. Okay. Um, so this can be proved. And why do we need this? If I have enough time today, or certainly Brendan on Tuesday, we'll talk about kind of relationship with inverse systems and van der Waals determinants, which is helpful. This is helpful for, but anyway, this can be proved using a lemma of, um, I'll just say Abe et al. Because there's a lot of authors. I can say out loud who they are: Horiguchi, Masuda, Mirai, and Sato. And they proved this when they were studying cohomology of Hessenberg varieties. So this is one of the many ways in which this project kind of like um, rhymes with Hessenberg varieties, but doesn't actually like intersect in like an obvious way. But it's a commutative algebra lemma. It basically says under some conditions, um, so A and B, okay, I'll use A prime. So if these are ideals generated by regular sequences, they call them Poincare duality algebras, and there's other ways of thinking about them, but last time we saw regular sequences, right? There are these lists of polynomials that only share a common zero of the zero vector. Um, um, if A prime is contained in A sub R, so this colon ideal, and if everything is of the right degree, so this is a very imprecise statement. But remember, if you're generated by regular sequences, then you know the size of the Hilbert series of the quotient is the product of those things. Basically, the degree of R is the difference between the dimensions of the quotients of A prime and A, roughly. Um, then, then in fact, they're equal. So we actually ended up using this lemma a bunch. It's really important for us for reasons that I think are still kind of unclear for us.
One tiny thing, R should not be an element of A.
Oh, thank you. Yeah,
So
something like that. Yeah. Um, so why is this useful here? Well, we have the setup, right? So we've got, we know this is generated by regular sequence. In fact, this is the regular sequence, right? And we saw last time that, so this ideal is also generated by regular sequence. So all we need to do is then check that let's see, that one um, I don't want to write this again, right? We just need to check this containment, right? And then we get equality. Um, in other words, that if we multiply any of these things up here by this polynomial, if we land in the usual invariant ideal, then these are equal. Okay. Okay. And how can we check this? Okay, I said I wouldn't write down again, but I'm about to. Take the generator, multiply it by this. I'll use K just to be a little bit careful. We need to check that this is in the usual invariant ideal. Okay.
And we need to check degree conditions, or are they obvious?
Yeah. So the degree conditions are basically exactly that. Yeah, I've been vague enough about them, right?
Right. So
so
the
it's
question
the
is it easy to see the degree conditions or not?
yeah. So what they are, I can say it is that R has to be a homogeneous element, and the quotients of S by A and A prime have Hilbert series, and these Hilbert series have top degrees. And the top degree of the quotient by A prime plus the degree of R has to
Has
equal
to
the top
equal.
degree of,
Okay.
yeah, and because of the way staircases are defined and the way this
It all works out nicely.
yeah.
Okay.
I mean,
Thank you.
roughly what's happening is that like this completes the lazy staircase to the full staircase is
Right.
it's
Right.
the right degree to do that. Yeah.
Exactly.
Yeah. So yes, I guess are these easy to check? Yes, is my answer. But um, okay. So there's various ways to check this. I thought that a neat way to do so would be to use orbit harmonics, which I can introduce briefly. Um, So this is a whole machine, but I can kind of give you enough of the machine. So if we take some finite set of points, we can define ideals. Think of this as, maybe call it the vanishing ideal. So this is all the polynomials that vanish on every point in the set. And then we can take these polynomials, might not be homogeneous. We can break them up into homogeneous pieces and take the top piece of each one. You can check that these are both ideals, and
Generated by the top pieces.
yes, thank you. Yeah, that's right. Now it's definitely an ideal. And then kind of the fundamental theorem of orbit harmonics um, is we have vector space, actually in some cases graded vector space isomorphisms. You can look at just functions on this set. You can look at quotients by either of these ideals. And right, the last one of these is graded. Often we're in a case where we have some group acting on these things, then we have isomorphisms as modules or graded modules, but I won't need that, at least right now. So it's a classical fact that if we take the symmetric group and we think of them in one line notation, so now these are, points like 1, 2, 3 or 1, 3, 2, dot, 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 right? N factorial many points. We can play this game and compute these ideals, and the top ideal is then this invariant ideal. So what does that mean then? We can use this if we can write down some polynomial that vanishes on all of the points in these n factorial many points, such that the top homogeneous component of F is equal to this thing. Oops. This thing. Well, then we take the top component, we must get something in this ideal, right? I'll just, I suppose the correct way to do this is to do something like this. Then we have the right containment. So this is kind of a fun game. I mean, I've grown to really like this machine. Can you write down a polynomial that kind of looks like this, but maybe with some lower order stuff that vanishes on all of the permutations? You can. So what can we do? So this thing, the idea is that so in any permutation, fix a position J, either n appears there, right, or its successor appears somewhere else in the permutation, either to the left or the right. So such a polynomial so let's see, times I'll be a bit sloppy about this. So why does this vanish on any permutation, right? So this is like if you take some permutation W, if Wj equals n, um, then that vanishes. Otherwise, Wj plus 1 appears elsewhere in the permutation, and then one of these terms vanishes. And if you squint at this, you can maybe see that by taking the top term, we lose this and this. And I claim that each of these appears in this purple circled guy up here, although it's a little bit, you might be a little worried about like this condition. My claim is that that gets kind of like filled in by these guys. The missing xi minus xj's appear later as xk minus xj's. It's maybe it's not obvious, but this does work. I'm happy to say more if people aren't convinced or just move on.
This is my first time seeing that. That's a neat argument. We did this in quite a different way in the paper. I'll say that.
I can tell you this argument I came up with Monday night. I woke up in the middle of the night because I had a different argument and I realized it was wrong. So
Yeah, yeah. I mean, I had actually proven it in the next section, but now I don't have to. So
perfect. Yeah.
If you wake up tonight and realize this one was wrong, just send us an email.
That's certainly a possibility, but the good thing is I'm done with my talk, so I don't have to worry
Oh,
about the problem.
okay. Right.
Um, yeah, I
Well,
mean, yeah, I think this works. Yeah, I guess maybe I should say a word. Why does none of this stuff appear in the papers? Because remember that this whole presentation of this ideal at the top was discovered afterwards. In the paper, there's a different regular sequence, P sub j's, P sub j1, P sub j2, which is kind of more naturally connected to this idea of a leading term. Um, but they're a little harder to write down, is really their only disadvantage. So I've been working with these guys instead. Okay. So the last thing I want to say then, I know I don't have too much time, but I can try to kind of lead into what Brendan will talk about next time is I'll say a little bit about inverse systems. The idea is that this colon presentation is going to be helpful, right? So why is that? Given a polynomial S, we have an operator given by well, you just kind of replace all the variables with partial derivative operators, right? Um, and this is a valid operator because partial derivatives commute and things like this. So, I mean, one example is, okay, if you do this to P2, you get um, the, what am I trying to write down? Right, this thing that you might have seen in calculus or physics or whatever. I'm writing this in an insane way, but okay. So this can be turned into an S module in the bilinear form. So then we have this O dot operator, which takes two polynomials and just turns the second one into derivatives and turns the first one into derivatives and applies it to the second one, right? So polynomials can act on each other by one becomes derivatives and hits the other one, right? And you get some other polynomial out. And then we also get a bilinear form where given f and g, you send it to the constant term of of this fx as derivatives on g, and you find the constant term there, right? So what does this do for us then? So this is a perfect pairing on each homogeneous piece of the polynomial ring, because the degree direct sum is orthogonal with respect to this bilinear form. This is not too hard to check. This all leads to what's called an inverse system. So given a homogeneous ideal, the inverse system, or Macaulay inverse system of this ideal, often written as a perp. So this is all the polynomials g that when we apply any f from the ideal to g, we get 0. Okay. And since we have a perfect pairing, we can decompose this into graded pieces, and we get that the dimension the ith graded piece of this is equal in dimension to the ith graded piece of this quotient. Okay. So I'm getting a little mixed up, but the idea is basically that if you have a quotient ring you want to look at, and you really only care about its graded vector space structure, you don't really care that it's a ring, you could look at this inverse system instead, and you get the same graded vector space information, right? And since I haven't really been multiplying in my quotient rings so far, I might as well try this, right? Why is this useful for our problem? Well, there's a result of Steinberg that I could probably just write this as I at this point, but if you take the invariant ideal and look at its inverse system, you get all the partial derivatives of the van der Maan determinant. So we'll write that as delta, but if you want something more precise, you get this guy. So it becomes a question of what's the dimension of the span of the partial derivatives of the van der Maan determinant of various degrees, right? This is a bit more concrete than looking at quotient rings, and then you're always worried about, things being equal mod the ideal or not, right?
So one thing I'll just remark, some people in the audience might be more familiar with harmonic spaces. So if you're
Thank you. Yeah, I haven't used that word.
Yeah, if you're associated with Adriana Garcia, you would call these inverse systems harmonic spaces, but
That's
if you're
right.
commutative algebra, they're called inverse systems. So
That's right. Thank you. I mean, harmonic spaces, like this example, is supposed to make you think about harmonics, sort of.
Adriana was an analyst at first, and I think gave an ICM talk in analysis.
So the last thing I want to say then is, okay, so this is a concrete way to look at the graded vector space structure of the quotient ring of this ideal using partial derivatives. So given our last result about this colon ideal, now what we want to do is to study what happens when we take all possible partial derivatives of not just the van der Maan, but let's see, we start by taking this derivative. Okay, so another way to say this is you fix some capital J, you take your van der Maan, given your capital J, you hit your Vandermonde with this partial derivative operator. And now you want to know what's the dimension of the thing I've got left, right? It's going to be less than n factorial. Um, the claim is that it's exactly this product of lazy staircase numbers, right? We've got a bound in one direction, but not the other. So this maybe makes this colon ideal idea a bit more precise, that this tells you which partial derivatives of the Vandermonde to look at if you want to look at these J initial ideals. And then next week, what Brendan will, I think, start with is extending this idea of inverse systems to superspace, right? So you can take some of these theta variables. It turns out they can also act by partial derivatives on superspace elements in a way which gives you a superspace module action. And we have this kind of result that we're building towards that tells you how to get the inverse system for SI from the original Vandermonde and some operators like these Euler operators or exterior derivative operators. Okay. But I think I'll stop there because I'm basically out of time. Any questions or comments?
Well, thanks for a great talk is one comment.
Any other questions or comments? Thank you, Jim.
It's really great to see this extension of the co-invariant story to this superspace. That just involves just a whole another kind of beautiful set of things.
Yeah, I mean, it really is reminiscent of, like Brendan mentioned, Adriano, things I learned from Adriano in my first class with him, or like early in your book, Jim.
Right, yeah. The harmonics this way.
That's right. Yeah.
I mean, you were kind of mentioning this earlier, Andy, but finding a more concrete connection to Hessenberg theory. There are lots of analogies that are going to kind of continue to appear throughout our lectures, but maybe finding like varieties, for example, that go with this story.
Yeah, that's right. One request I wanted to make, which I always give is something I haven't talked about, is that the usual invariant ideal comes up when you're looking at cohomology of flag varieties, right? Is there some geometric way to get to this ideal? It sure seems like it's some, sub-variety of quotient or something of the flag variety, but we haven't. I mean, there are certain things we can say in that direction. Maybe Brendan will get to them at the end of his series, but nothing as simple as like, this is the cohomology of blank, or its quotient is the cohomology of blank.
There's also this fact that the Carlson-Oblomkov basis for the diagonal covariant ring in their latest rendition of their preprint, they show that there's a way of like a Hessenberg variety identity, which when you specialize everything becomes the schedules formula, basically. So
And actually,
products of yeah.
Right, and
Yeah. So
as a matter of fact, when we get to Solomon-Terao theory, we're going to see an analogy there, where after they perform one filtration, they make this kind of assertion that they get a basis in one set of variables, right? Kind of coming from a Hessenberg function.
yeah.
And from our perspective, the result that they cite is really saying that you have a basis for a certain family of Solomon-Terao algebras corresponding to ideal subarrangements of the type A braid arrangement. And we're going to be working with more general southwest subarrangements. So there's kind of even more analogies to the Carlson-Mellet story. And I guess that'll probably be in my not the next lecture, but the lecture after, where I do prove the Sagan-Swanson basis conjecture.
Uh-huh.
But yeah. So there are these, again, a lot of the same machinery. But so sorry to cut you off, Tim. Sorry about that.
No, that answered my question. Absolutely.
Yeah, I think roughly the idea is next time Brendan will talk about inverse systems in superspace, and then the time after he'll come back to hyperplane arrangements. And this is what I've got here is like is a case of Solomon-Terao theory, but he'll go deeper into that to use to prove that the basis is correct. Right.
Mhm.
Cool.
Okay, any other questions or comments? If not, we'll thank Andy again and look forward to Brendan on Tuesday. Okay.
Thank you all very
We'll
much.
keep the web page updated with videos and things. Okay. All right. So long, everyone.
All right.